Any questions? Okay. Let's continue on our quest of reality versus belief. So we've established that there's a nucleus to an atom based upon Rutherford's experiment. And they haven't quite figured out electrons yet. They know electrons are hovering around it. And so let's just do a little bit of physics 151 here. Force diagram. What are the forces acting on the electron?
Weight coming down.
Let's assume that the weight of the electron is insignificant.
There's no friction.
Correct?
I forget if magnetic was 151.
You forget what?
Magnetic force, like, is it like pulled by the nucleus?
It is pulled by the nucleus, otherwise it would be going off in a straight line. But it is not a magnetic force. Other people can play besides Jack. All right, this force is from 152. Day one.
Electric.
Yes, yes. It should not have taken that long, but I appreciate it's coming in. All right, so we have this electric force. Now, the electric force acting on the nucleus, again, the nucleus is so much heavier than, or bad wording, so much more massive than the electron is that we're not worried about. We're assuming that the nucleus is still. All right, so we got this electric force here. Plug in F equals ma. What's the formula for the electric force?
K Q1 Q2 over R squared.
Yes. So the Coulomb's constant, we'll see there, times Q1, Q2 over R squared is equal to mass times
Acceleration due to gravity.
No. It's not in free fall. This is a 151 concept, although we have talked about it in 152. Hint, the electron's traveling in a circle.
Or the distance between the two. Like the radius, I guess. Oh,
It's got to be an acceleration. What is the acceleration associated with things traveling in a circle?
centripetal?
Yes. So what's the formula for centripetal acceleration? We're cruising right along here. are times I think, do I really need to give the formulas on the first page?
They're very beneficial.
I think I'm enabling.
I think you're benefiting yourself, because if they weren't there, that'd be a lot worse.
It's something with angular velocity. I don't know.
There are two formulas. One with speed and one with angular speed. Did you find it?
No.
Okay. V squared over R. Sorry to spoil it. Hopefully that rings a bell at least. I'm not looking at nods or anything like that. It seems like it not ringing a bell.
No, definitely the first part. The K.
AM?
No, the KE Q1, Q2, part 2.
Okay. All right, so the two charges here are the charge of an electron, which I'll just label as E, and the charge of the nucleus, and let's just keep it simplified. Let's assume this is a hydrogen atom, so I'm only dealing with one electron, one proton, and so E squared over the radius of the orbit. Actually, that's going to cancel out with that one, and so that's going to be equal to mv squared.
This is the electric force for one electron.
This is, at this point,
Yeah.
this is just a reduction of this equation right here. The charge of the electron is E. Oh, that's where you're going. E is used a whole bunch. There's Euler's E, 2.718 and so forth. There is the electron, which is symbolized by the negative sign there. And then there is E, which is the charge of an electron, the 1.6 times 10 to the negative 19.
And that one is the charge.
Yeah, that's the one we're working with right here. The minus sign, I don't bother writing down because the negative sign is ultimately telling us that it's being attracted, and I've already taken that into account, the fact that it's inwards. It's a centripetal force. All right. So all of this, and this is all classical physics, there's nothing special here. We have centripetal motion of sort of the planetary model of an electron orbit. So Bohr is, and if you continue with along this path without bringing in anything quantum, you get that the electron should eventually spiral into the nucleus. However, Bohr makes a proposal. He says that the angular momentum, there it is, the angular momentum is quantized. And he says it's going to be some multiple of h bar. Now we did h yesterday, it's Planck's constant. H bar is just h divided by 2 pi. It shows up enough that they came up with a special symbol for it. Now it's usually presented in the textbooks that he comes up with this proposal. It leaves out probably the months or years that he spent thinking about it until he came to this conclusion. And I'm always curious about how he comes up with this. It's like Rutherford's experiment. It's talked about he was just testing to see what he'd find out, and he found a nucleus. And it seems like he had to suspect that it was there already. So anyway, angular momentum. What do you remember about angular momentum?
2 pi f. No, that's
That's it.
frequency. Or angular frequency.
Indeed.
You said angular velocity.
Angular momentum. Well, let's drop, what's momentum?
Mass times velocity.
Pardon?
Mass times velocity.
You threw me because I was just expecting the letters.
Sorry.
All right. So it's mass times velocity. So we're talking about angular momentum now. Flashing back, what is the angular analog of mass?
Is it just mass?
No, it's not just mass. Oh, it's been along several months, hasn't it? But Mike is looking it up. He'll come up with an answer real soon here.
When you say analog, what does that exactly mean?
If you recall back to when we first started doing rotational motion, is that we basically can transliterate that acceleration is the change in velocity over the change in time. Well, angular velocity is the change in angular velocity, angular acceleration, angular velocity over time. That there are all the formulas where we had A in it and V in it and T.
Mm-hmm.
We can just substitute alpha, omega, and T into it and get the rotational
And
equation.
that is why it is called an analog.
Yeah.
The moment of inertia.
Say it again? Oh, yes, indeed. It is the moment of inertia times, what is the angular analog of velocity? All right. Moment of inertia. What is moment of inertia?
Rotational inertia.
Yes, you are correct. Formula? Okay. Remember that when you're dealing with rotational motion, that if I'm closing the door, the more mass that is farther away from the axis, the harder it is to get moving or to stop it. So it is, you basically add up all the little m's and r's squared. So if I have a disk, then I will ultimately use calculus, but you're in essence taking every little bit of, you break it up into an infinite number of tiny masses, and then take the distance from the axis of rotation to where each mass is, and you add them all up. Now, there's some shortcuts you can take, which we did. However, in essence, it's you add up all the masses times r squared. Well, an electron is considered to be a point mass. So it's not like I'm breaking it up into an infinite number of masses because it already is infinitesimally small. So the moment of inertia of the electron, hovering about this central point, is just mass of the electron times r squared. Back over to here. So we have L is equal to NH bar is equal to H divided by 2 pi. And this, my angular momentum, is going to be equal to the moment of inertia times the angular velocity of the electron. Well, as I wrote over there, the moment of inertia is just the mass of the electron, r squared. And angular velocity, all right, get to ask you another question here. What's the relationship between angular velocity and velocity?
They're both speed. They're both speed.
Okay, I'm looking for a more mathematical relationship.
Divide by 2 pi or multiply by 2 pi? I don't ever remember which one.
That is wrong way to go. Let's see, can I work with that? No, let's do it the old, we'll go the long way. Why not? What's the relationship between arc length and angle?
It's,
Theta, some, hold on.
This is a math question, not a physics question. Comes from how radians were defined. So I got a radius there, I got an angle there, I got an arc length there. What's the relationship between those three quantities?
Oh, the arc length, or the arc length is equal to theta r, or r theta.
Yeah, S equals R theta. So the change in the arc length is equal to, well, in essence of the arc length, is equal to R times that angle. If I divide by time, so what is delta S over T, delta T? In other words, that length divided by time.
say that one more time.
If you've got a wheel rolling, basically the distance that it rolls is equal to the arc length that touches the ground.
That's its angular frequency.
No.
It's its
So
frequency.
this is a distance
That's
divided by time.
meters per second.
Pardon?
Meters per second. That's
Those would be the units.
Oh, speed.
Speed, yeah. Is equal to R times what is delta theta over delta T?
Angular speed.
Yeah. So V equals R omega, that's the relationship I was looking for over here. And so there's my moment of inertia times omega, which is just V over R. So what we end up with is, well, that cancels out with one of those. We have the angular momentum of an electron is just mass of the electron times its speed times R. Again, this right here is the novel approach that Niels Bohr is taking.
Niels Bohr.
Niels.
Niels.
He couldn't be normal and spell it with an
What's that?
A. He couldn't be normal and spell it with an
I suspect that that was normal for his Denmark.
Or his Denmark.
His Denmark.
A. He's the king.
All right, so from this relationship here, if Bohr is correct, then we can solve for V, we can plug into our relationship right here. So therefore, V is equal to N times H bar over mass, all the masses are mass of the electrons, so I'm just gonna drop this subscript, MR. Now, oh, I never actually said what N was. This whole idea of quantization is that there's some tiny amount that things increment by. So N right here is equal to 1, 2, 3, 4. In other words, the angular momentum is some multiple of this.
No,
This quantity right here.
that's an H with
Yes, called H bar.
H bar.
If you're among physicists and you say H bar, it's not a drinking establishment, it's that. So if I plug into my equation over there, I have Coulomb's constant, and I'm gonna put it in the epsilon form. So 1 over 4 pi epsilon sub naught, that's Coulomb's constant. E squared over R equals M in H bar over MR, that quantity squared. And then from that, we get 1 E squared. And again, this E right here is the charge of an electron. over 4 pi epsilon sub naught equals n squared h bar squared over m r. One of these masses is gonna cancel out with that one, and one of these r's will cancel out with that one. That's why it's just m r on the bottom.
And that epsilon sub naught is the free space there?
Yes, that is the permittivity of free space, the 8.85 times 10 to the negative 12. All right, so if we solve for r, r is equal to charge of an electron squared over 4 pi epsilon sub naught times the mass of the electron over that's right. Sorry about that. That is the product of a fevered mind. So r is equal to n squared h bar squared over m e squared and then 4 pi epsilon sub naught. If I take, and I keep glancing at my notes just making sure I haven't made a careless error. All right, so what I'm gonna do is I'm gonna rearrange it slightly, put it in a more traditional form. So the radius of the orbit, you're now setting up so that the radius of the orbit can only be certain values. It can't be just anywhere. And so this would be equal to 4 pi epsilon sub naught h bar squared over mass e squared and then times n squared. Everything that I have in parentheses there is a constant.